I've had some questions recently about make and makefiles and how they work, and so I thought I'd take a little time to either introduce you to make and makefiles or to review what you've maybe seen previously but haven't paid attention to for a while. The idea of a make is it's a program that allows you to establish dependencies among files that are going to be used to construct other files, basically. So when we're talking about a compiled language like C or C++, it's often the case that we're going to have to run the compiler to convert the source files into object files or libraries or executables. And that process can be sort of tedious and time-consuming and error-prone if we're doing it all manually. In particular, one of the things that's challenging about that is remembering, which files do I need to recompile, which files have I changed. And make takes care of all of that dependency information. So instead of trying to remember which specific compile commands to run, you basically just type make, and make will do the right thing to build all of the executables that you've defined, or the outputs that you've defined, which could be executables often, or libraries or object files, based on the input files that have changed. And it will do its very best to do a minimal amount of work. It'll only compile those things that have changed relative to the last time they were compiled, and minimize the time and number of commands that need to be executed at any given point in time. So in order to configure make to do that job, we need to create what's called a makefile, and we'll talk in detail about what those makefiles look like and what the syntax is and so forth. But to get started here, let's just create a really simple hello world program. So I'm going to just call this hello.c, include studio, and then define a really simple main function. Doesn't take any arguments and just does printf hello world, and we're done. So if I now go back out to, or if we go to shell here, you can see here that we just have hello.c in our working directory. Now we know that if we want to create an executable from this, we can say cc hello.c, and that runs. And what do we get for the output? Well, we get this really oddly named file called a.out. That's just the default output that the compiler will create for us. And if we run that, get hello world, as we'd expect. Now I'm going to get rid of that a.out file. It's pretty uncommon to just use a.out as our output name. So another way of running the compiler that gives us a little bit more mnemonic name for the executable is to use the -o flag, which stands for output, obviously. And we can give it a particular name and then run that. And now we see that we get hello.c, and then hello is the output file. The asterisk after hello there is just an artifact of the way I configure ls. It's going to give me some additional characters to mark what type of a file it is, in this case an executable. So now if I just run hello, we get the same output, right? That's the location of the executable. What we've basically created here is a dependency, right? We know that hello, the executable, is dependent on hello.c. And what a makefile allows us to do is express that dependency and tell make what commands to run to create the target, the hello executable, from the source file. So let's go up here and make a simple makefile. So a makefile has, most of what's in a makefile is going to be what are called rules. And a rule has a specific form. It's going to be some target file, usually a file, and that target is going to be dependent on a set of dependencies, which normally are other files. And the additional information that's supplied in each rule is some commands that are going to take the dependencies and create the target. So this is usually called a recipe. And recipes can have multiple lines. You can run multiple commands that together create the target from the dependencies. It's also important here, if you're making a makefile from scratch, that this has to be an actual tab character. So the target always has to appear at the left margin, and the recipe commands have to be indented by a tab. And it's got to be a tab. Make is kind of anal about that thing. Now, that's not a legitimate, well, yeah, that's not a meaningful make command. So I'm going to comment that out. I'll leave it there for your reference. Now what we want to do is create a rule that tells make how to build hello from hello.c. So in this case, the target, the thing we want to build, is hello, and it depends on hello.c. And the way that we convert hello.c into hello, the recipe, is to run the compiler. And I'm just going to totally crib from here and just grab that command that I typed in before and use that as my recipe, right? So this says to create hello, you need to have hello.c, and what you do to get from hello.c to hello is run that command. So now we still have our hello file there. So let me remove that to start with. And then, so now I only have the hello.c file in my make file, and now I'm going to type make hello. So on the command line, I tell make what target do I want you to build. You can actually include multiple targets on the command line. And because there can be many targets in the same make file, we've got to tell make what it is that we want it to build. So make hello, and you can see that make tells you the commands that it's executing as it executes them. And if we look in this directory again, we'll see that we have our hello program back again. If I run it, it still says hello world. Notice another thing about the targets and the dependencies. So I'm going to do an ls-l, which is going to give me a long directory listing with the modification times. And I'm also going to give a -t flag. You can do it like this, but because they're single letter commands, you can actually join them together into one kind of composite flag. The T says sort these in reverse chronological order. So you'll see newest at the top and oldest at the bottom. So we see here is that in the ls output, the hello program is actually the newest file. And then the make file, because that was the one we modified before that. And then hello itself actually is like 5 minutes older than, or hello.c is 5 minutes older than hello. So if I were to run make again, make hello, make says, hey, we've already got a hello, and it's up to date with respect to all of its dependencies. In other words, hello itself is no older than any of the things that it depends on. Now if I went into my hello.c file to make a modification, hello make, save that back out. Now if I go back out and here and do my ls-lt, we'll see that now the newest file is hello, and in particular it's newer than the hello executable. So at this point, the hello executable is out of date with respect to hello.c. It's older than one of its dependencies. So now if I type make hello again, it won't just say hello is up to date, it'll actually rebuild it, right? And again, if we look at the ls-lt output, we can see now the hello executable is newer than hello.c. So because hello.c is the only dependency of that target, we know that hello itself is now up to date with regard to all of its dependencies. And if I run hello now, it's going to say hello make. Now that's all fine and good, but so far we aren't really seeing much of an advantage to using make. We've just added the complexity of creating a make file. Where make really shines is when we get to more complex builds, where we've got dozens, hundreds, thousands of source files that we need to be able to manage and keep track of and establish the dependencies among them and make sure that when we rebuild the system, we're rebuilding everything that needs to be built. So let's come up with a slightly more complex example here. I'm going to create a new source file called main.c, and it's going to have our main function in it, as you might not be surprised. And inside of here, we're going to call a function called greet. And I'm going to pass greet the word world. And that's all I'm going to put in here. And I'm going to create another file called greeter.c. And this is going to do some output, so I'm going to include studio.h and define a function called, as you can be surprised, greet. And it's going to take an argument, let's call it who. It's got to be char star. And it's going to say printf hello %s new line and use who as its argument, and that's it. Now what I want to do then is compile both main.c and greeter.c, and I want to link those two output or those two object files together to form a new executable. So let me go back to our makefile, and I'm going to add a new target. So a second rule here in the makefile. Although the rules can make use of one another, they don't have to. It's just basically creating an arbitrary graph of dependencies between files. So in order to avoid overwriting my hello program, I'm going to call this one hello2, and I'm going to say that this thing needs to depend on main.o and greet, what did I call it? Greeter .o. Now notice that I'm not making the output dependent on the C files. I want to actually create the independent object files to show some more functionality of make. And let's just stop right there and go and run make. Now I can still make use of the make for the original hello by giving that as the target, and of course that's still up to date. If I want to compile, or I want to create the target hello2, I can say hello2. And now I got some issues here. So the compiler's telling me that I need to clean up some of how I'm using this greet function. There's an implicit declaration of function greet, and the C compiler doesn't care for that. So let's go and fix that up. What we want to do is create a header file that allows us to make use of the greet function from other source files without the compiler grousing. So let's create a new file, call this greeter.h. And what I'm going to do is I'm going to declare that greet function inside of here. So a simple way to grab that at this stage is to just load in the C file and skinny it down to just be the declaration of that function. So now I've got a declaration for greet in a header file, and I'm going to make use of that in both of my other source files for different reasons that I'll explain in a second. So inside of greeter.c, I have to include studio because I'm calling printf, but I'm also going to include greeter.h, not greeter. What that's going to do is read, and let me just bring up that greeter file, or that header file. So that declaration is what I'm saying is the definitive declaration for that function. Anybody that wants to call that throughout my massive software system here is going to need to call it with that signature. It's important though to include that declaration in the file where you're actually going to define the actual function, because you want to make sure that the actual function corresponds to the declaration itself. So I'm going to include greeter.h in the greeter.c file, but then I'm also going to go and include it in my main.c file, because here's where I actually call that function. And this is what the compiler was grousing about from before, is that it just saw this file or this function that it didn't know about. And by bringing in the header file, we now see that that's the specific definition of this function. So now I'm going to go back out to my shell and try again. Make hello2. I think I probably forgot to save some files here. Yep. Try again. Okay, now we see that we get these two files being compiled properly, and we've gotten rid of those error messages. Now let me show you what's in our working directory now. I'll just do an ls-lt again. So you can see here's our greeter.c file, our main.c file, and our greeter.h file, right? All three of our source files. And what we've created so far is greeter.o and main.o. Right? None either of those is an executable. It's just the object file that comes out of the compiler when you're compiling a single file into its output. Now that's fine, but we actually want to create an executable here. So let's go back up to our makefile. And let's just think about what's going on here so far. So I've said make hello2. And I told make that hello2 depended on those two object files. Now, somehow, magically, let me get rid of those object files again so we can see this make work one more time. So make hello2. Well, somehow make knew how to compile the source files that it found into these object files. And in particular, it knew to create main.o, it should compile main.c. And to create greeter.o, it should compile greeter.c. And it knew how to create this output. It's using the -o just like we did for our executable, but in this case, the output goes to the .o files. And it also supplied this -c flag, which basically tells the compiler to go ahead and do the compiling, but not to try to link anything together to create an executable. So how did make know about that? It turns out that make has the ability to define what are known as wildcard rules, where we can basically say something to the effect of, to make something.o, if you have something.c, run a compile command that looks like this. So we can define our own default commands, but for a lot of things that are really common in the Unix environment, make just has predefined rules that know how to take a .c file and make a .o file, for example. So that's really cool because a lot of those common cases are already taken care of for us. And if we need to do something more specific or something different from the default, we can also redefine those things. But that's a little outside the scope of this little presentation. So we're leveraging make's built-in rules to turn the .c files into .o files, but we haven't actually completed creation of that final hello2 program. So what we're going to do here is add our own recipe command where we're going to run the compiler again. Remember that CC is kind of a compiler runner program that does different kinds of things. And in this case, we want to create hello2. And to create hello2, we need to link together those two object files. So I can name them on the compile command in the recipe, main.o, greeter.o, and then we're set. So now, again, I'm going to go and get rid of those .o files so that we're forcing all of the command steps to build. Remember, in the previous case, we only ran these two compile commands to make the .o files. And now, when we do this again, we'll see we reran those same commands because I deleted the .o files. And then we also ran this command from our recipe up here, right? It's exactly that command that got executed. And now if we look in our directory listing, we'll see that we have at the very top there, hello2, which is the executable version, the linked version of greeter.o and main.o, plus the stuff that got brought in from the standard library like printf. So at this point, remember that our main function asked us to say hello world. So if I do hello2, I'll get hello world. That's not super interesting, right? What I want to be able to demonstrate is that I can make a change to that argument and see something different coming out from my greeter program. So let's say hello makefile. Now run hello2 again. Oh, same thing. I forgot to build, right? This is actually a pretty common thing here. Even when you've got something as helpful as make that's doing your builds, you got to remember to run it. So what I often do is I'll run make and then I'll run the program. Now one way to do that is to just use a semicolon in bash that just separates individual commands, and then I can just say hello2, okay? So it'll do the make and then it'll run the command. So you can see here, hello is up to date, hello world. What's going on there? Well, I'm making the wrong thing. So you got to be careful to be, particularly as your makefile grows in complexity, and we have a really simple one so far. I want to actually make hello2 and then try running hello2, okay? So now we'll see here, I had changed main and only main. I didn't make any change to greeter.c. So you'll see here that make, using its built-in rule for compiling to an object file, rebuilds main because it detected that main.o was now out of date with regard to main.c. Greeter didn't have that problem, so it didn't rebuild it, and then it ran my linking command from the makefile, and that completed the build, and then it ran hello2, which gave us hello makefile because I had changed this argument to makefile. Let's do a little bit, we'll do another thing here that will illustrate that or give you another chance to see that again. Let's say we go back here, and again, I'm going to change main.c. So let's add in our command line arguments, argc, argv, and then we'll say if argc is greater than 1, in other words, we give it an argument in addition to the name of the file that's being executed, we're going to say greet of argv of 1, else we'll greet with default. Okay, again now I'm going to do this same command, make hello2, and then run hello2. Same behavior. I made changes to main, so it recompiled main and it relinked, and then it's now saying hello default, right? Because I didn't give it any arguments on the command line. If I do this again, and now I'm going to say foobar baz, so that's going to be argv of 1. Two things going on here. One is we actually do see hello foobar baz coming out. The other is that make already figured out that hello2 was up to date, right? So even though I'm adding in this make command just as a kind of a habit to make sure that everything is up to date before I try to execute it, make is pretty quick to figure out that there's nothing that it needs to do, and so it doesn't really add any additional time or whatever to your development process by just doing rebuild as a matter of course. You don't have to do that, but more than once, obviously we just saw earlier, I got bit by not having done the recompile. If you're going to do that, let me suggest one refinement here. Instead of just separating the commands, you can use in bash something that looks a whole lot like the C language logical compares or logical operators. So when I say ampersand ampersand in here, I'm basically telling the shell, run make, and if it works out okay, if everything comes back fine, do the next thing in the command, run the executable. What this does is allows you to verify that the build worked successfully before you go on and run the command. That's what the ampersand ampersand does. You recall that when you run a command in Unix, the main function can either, well, the main function can return a value, or you can call exit explicitly. And if you return a 0, say, from main, or call exit with 0, that's by convention an indication that the command ran successfully. And if you don't want to, or if you want to indicate that something went haywire, you can return a non-zero value, a positive value, usually, because there's usually a bunch of different ways things can go wrong, but only one way that it can go right. This ampersand ampersand thing is testing that return value from the command that just ran. So if make succeeded, it will return 0, and the ampersand ampersand will say, hey, everything's cool, let's do the next command in series. And you can actually string these together if you want. But if something went wrong with the make, then the ampersand ampersand will see that make returned a non-zero value, and it will short-circuit the execution of the rest of the command. So in this case, it's not a big deal to rerun hello2, but it is a little bit misleading if you miss the fact that the compile caused an error, and then go ahead and run the old version of your code and think that its behavior hasn't changed. So this is a good way to avoid that. Let me just illustrate what I'm saying here. So I'll just do this again with everything working good, and we can see that, well, hello2 was already up to date. We can force a recompile by just getting rid of, let's get rid of greeter.o this time, just to illustrate that it knows how to tell which is which. And then we're going to run that command. Again, it behaves exactly the same as before, except now it's got to rebuild greeter.o from greeter.c because I removed the o file, then it relinked, and then it ran my program. But let's go up here and intentionally put in a syntax error. Right, that's now bogus C, which means that the compile is going to break. So if I run this again, you can see here that we tried compiling main.c and that didn't work out. But notice what doesn't happen. We don't see hello foobar baz here at the end of this output. Although hello2 is still out there, right? Because the compile failed, that old executable is still there. If we use our ls-lt, we can see that main.c is newer than hello2 because the compile failed. So we've got here a broken version of main and an old version of hello2. And if we were to just use this syntax by putting a semicolon in here, the compile is going to fail again because I didn't fix the main.c file, but it's going to run hello2 anyhow, right? So that semicolon just means split these things apart. But it's better to use the ampersand, because then if the compile doesn't work, we don't erroneously run the executable thinking that the compile worked okay. This isn't difficult to detect again here when we only have one or two files that we're compiling. If we have 1,000 files and one of them fails to compile, and the compile error messages have long ago scrolled off the screen, and then we run our executable thinking that it rebuilt successfully, we're going to have to backtrack and figure that out and notice that happened and stuff, which is sometimes painful. So I'm going to fix this again and then rebuild. And now we get a functioning hello2. And if we check our file times, you can see that hello2 is now the newest file in the directory. Let's talk about some creature comforts that are often added to makefiles to make your life as a developer a little bit easier. One of the things that I've been doing here throughout is removing the output files from the make process so that I can try remaking from scratch. That's a pretty common thing to do, and what's usually done in a makefile is you'll define a target called clean, and it's not going to have any dependencies, so it's a kind of an unusual target. And there's not going to be an actual file called clean. So it's still going to be something you can ask make to build, so-called, but it's just going to be there to run some commands. So we can put in here, for example, rm to remove files. We'll put in -f so that it doesn't freak out if, I don't think -f stands for freak out, but it's not going to freak out if we're asking it to remove files that aren't there. So if we do the clean and then we do the clean again, it's not going to grouse at us. And let's just go back down here and take a look at some of the files we might want to get rid of. So we could certainly remove hello and hello2, right, which are the executables that we're building. We probably could also live without the .o files. And here in what you're seeing in this file, or this list of directories, this files that end in a tilde. That's actually, I'm using Emacs here, of course. And Emacs, if you're not using revision control, which I'm not for this little tiny example, Emacs will create a backup file every time you save a file. So you have your most recent changes, and it'll name that file the same thing as the original file with a tilde at the end. So I don't probably need to keep those backup files around, so I'll say let's delete that as well. Now if I go down here and say make clean, right, I'm still naming the target I want to execute. It's going to run that remove command, and then you can see here that now those files are gone. One interesting aspect of this is that normally the files that get left behind after you do a make clean are the same files you want to put in revision control. When you're working with Git or some other revision control system, you only want to put into revision control those files that are the sources for other files, whether that's a SQL file or a data file or a source file for a program. You don't want to check in the outputs of the build process. So you don't want to check in .o files or .pyc files or executable files because that's just sort of a waste of space and time in the repository. You want to just be able to have access to those files that are necessary to build the thing from scratch. And normally the flip side of that is the things that you're not building from scratch are normally going to be included in your clean target to get rid of that extra cruft that you don't really need to have hanging around except when you're actively working on that particular piece of code. So now having done that clean, I can say make hello, and that'll build my hello program. I can make hello2, and that will recreate everything. Now let me also illustrate that you can ask for more than one target at the same time. So I'm going to say make clean, and that restores me back to just my source files. And now I can say make hello and hello too. So now it's going to make both of those commands. So the first command was building hello directly from hello.c. Then here's the two compiles of the assembly or the .o files and the link at the end. And now I have the both hello and hello too. Another common approach to doing a build like this would be to do a clean first and then build the other executables. So you can name multiple targets on the command line, and make will attempt to satisfy those requests for targets in the order that you give them. So this is going to cause clean to run first, and then it's going to rebuild my two executables. There we go. We see that at the top here we've got that rm-f that throws away all the old stuff and then rebuilds everything from scratch. So this is, again, it's not a big deal here with just a few source files, but in a larger software system where you want to sort of be sure that you're getting all of your compile stuff working and you're bringing in all the latest and greatest source code from your code and maybe other libraries you're linking in and stuff, having that clean command is a really handy way of ensuring that you're getting a full and complete clean build of your code. Another convention that's often observed in makefiles is, well, let me illustrate this first. If I just say make, I'm going to get hello is up to date, right? Let me do a make clean again, and then I'm going to just type make. You can see that it's only operating by default on the very first dependency, or the very first rule is what make will do by default. That being the case, it's oftentimes in a more complex makefile, you'll define as the first rule something like all, and then say, let's say that the executable that we're working on right now is hello too. That's a little misleading, I guess, to say all and just listing one file, but the idea here is to give a definition of the very first rule in the file that points to the things that you just want to build by default. You could also call this, maybe be better to call this default, right? So now if I just say make, the first rule is now that default rule, which says that it wants to have hello to built. So hello to is now going to be compiled and linked by just saying make. So there's the two compile commands, there's a link command to generate hello to, and now, hello to foobar is the one that gets built. Now if I'm working along and I'm not actively working on hello to, but I'd rather do hello, now I can do just make with no arguments. Turns out that that's already built. If I do a make clean and then a make, it's going to build the hello file. And as I suggested before, you can also create, and it's common to create, let's leave this hello to, it's also common to create often earlier in the file here, so it's evident when you're first reading the makefile, a command or a target called all, which is going to say list all of the things that this makefile knows how to build. So hello and hello too. Now if I do make clean, I get rid of all of the extraneous output, and now I can just say make all, and it will build both hello and hello too. So that's a convenient and common way of listing multiple targets in the makefile. Finally, it's also possible for us to use what amount to kind of constants. They're really kind of a string literal macro, but let's say that we're compiling on different machines at different times, and on one machine we want to use the native C compiler. I'm working on a Mac right now, so it's running the standard Xcode C-lang compiler. But I might want to, for example, make use of a different compiler. If I switch over to Linux and I want to use GCC, or I've also got GCC on this machine, it'd be handy for me to be able to specify that easily. What we can do is define what's called the macro in make, and I'll start out by just kind of making this behave exactly the same way. So I'm going to define a macro called CC, capital letters, which is kind of the convention, and I'm going to define that to be CC. So not anything particularly interesting here, but what I want to do now is use the value of that macro as the name of the compiler that I want make to run. So throughout this file, I'm going to change CC to $CC, which is, I'll come back to that in a second. So what this syntax says is that I want to replace that $ thingy with the value of that macro that's inside there, with the value of CC, which in this case is just CC. So this is going to look exactly the same from the outside. So I'm going to do a make, I'm going to do a make clean and then a make all. And to no one's great surprise, it runs CC a bunch of times. However, if I wanted to compile this with GCC instead, I just change it in one place, and now CC, capital C, is defined to be GCC. And if I go back down here, now I'm gonna do two commands here. This is also a really common idiom when you're using make, is to say make clean and then all. Right, so it's going to remove all the old outputs and rebuild everything from scratch. And we'll see that the compile command now is GCC instead of CC, which again makes it really easy to sort of reconfigure things as we go. It turns out that I alluded earlier to the notion of kind of built-in rules that make has, and its built-in definition for C is actually the CC command. So you can even remove this altogether and just use the makefile as is. I'm going to do that clean all again. You can see that it reverts back to using CC as the compiler, because that's, again, one of these built-in make rules. So here we're overriding it to the same value, right, when we're using CC, but more interestingly, we can override it to use a different compiler entirely. Another really common macro that's defined for C programs in make is called C flags. And this can be used to supply additional arguments to the C compiler at the time that it runs the compiler. And one of the things that I always do when I'm working in C is I want to turn up the error messages in the compiler to their maximum extent. And that's done by saying -L all. So I want to have that on all the time because I want to have it give me all the warnings it can, because the compiler is smarter about C syntax than I tend to be. In addition, I usually set another flag called WError. And what that does is says if any warnings get generated, the compiler can generate warnings that are just kind of informative. Hey, you might want to check this out. It also, in some cases, is going to just come upon a bona fide error that prevent it from continuing to compile your file. If it just gives you errors, it'll keep compiling and it will generate the output. So you'll end up with the .o file or the executable file as appropriate. And that means that you're going to have some issues in your compile, but you're essentially ignoring them and moving forward anyhow. That is most of the time a recipe for disaster. So what the -W error flag says, hey, if you find any warnings, treat them as if they were errors, in the sense that it's not going to actually generate any output. It's just going to give you all these warning messages and then not do anything else. So you're not going to end up with a .o file or an executable that's based on code that created a bunch of warnings. It's just not going to be there. So you're not going to be tempted to go ahead and use that or run it, or maybe miss the fact that there were some issues with that compile if you're compiling a bunch of files and the errors all scrolled off the screen. So by setting the C flags macro to these two flags, I feel like you get really good error checking as part of the compile. So I'm going to head back down here and do that make clean all again, and we'll see that now when the compiler runs to compile the C files into the O files, that having changed that C flags macro to include those two flags means that they're included there. Now notice that it only shows up in these two GCC commands. That's because the C flags, which is defined to have these WL WError, that value is being used behind the scenes in this predefined rule that make has that knows how to compile a .c into a .o. However, for these other two GCCs, you notice that those flags are not there. Well, that's because we have specified explicitly the command that's going to be run in the case of building hello from hello.c or hello2 from its object files. So if we want to be consistent here, we need to actually say, let's include C flags in both of those cases. That's basically the way that those rules, those implicit rules for the compiler, are defined by make itself. Now if we go back and rerun, again we're going to do a make clean and a make all to to force everything to recompile, we'll see that we get a consistent take on all of those C flags. One final thing to mention here is that we're kind of crossing the streams in a way with these targets, right? We've got some actual targets that are going to turn out to be real files like hello and hello2, but we've also got these other targets that are really only there sort of for our convenience as developers. And if we ended up using a file that happened to also have the name of one of these kind of convenience targets, that could cause some problems. Because make would say, hey, the developer's asking us to do something with this file called default, and oh, by the way, there happens to be a file called default, let's do something with it. We might want to avoid that, so there's a little subtle addition to makefiles you can add. There's some predefined targets that all start with a dot, and one of them is called .phony, and that basically just says, hey, here's a list of dependencies that correspond to targets that don't have any real meaning. They're just phony targets that we're defining for the convenience of the developer, and don't go try to find files with these names and figure out how to build them. So in our case, the phony targets we've got defined are default, all, and clean. So by just indicating to make that those are phony targets, make won't get confused if we happen to introduce a file that has one of those names. Again, the behavior is going to be exactly the same as before. We can clean and remake, and that's going to work just as we'd expect. One thing you might have noticed here in the current makefile is that we got a little bit of redundancy in some of these rules. So hello2 depends on main.o and greeter.o. And in the compile command, or the link command here that we're defining, we're basically repeating that same information and saying, hey, the thing on the left-hand side of the colon, the target, depends on the thing on the right-hand side of the colon. And there's some shortcuts you can use that make that a little bit less repetitive and a little bit less subject to issues. So for example, you decide to factor your code into an additional source file, you've got to remember to come here and update the source file in the dependencies, and update the object file in the targets and so forth, in the recipe. Let me just show you another way that can be done. I'm going to define a new output that's still going to be dependent on those same two files. So this is redundant, but I just want to illustrate a different syntax without blowing away the one that we've already talked about. There are some what are called meta variables in make that start with an @ character, and sorry, that's the dollar character, and one of them is $@. And in make, that means the thing over here on the left-hand side, the target. Similarly, we can refer to the things that are on the right-hand side, the dependencies, with $up. Now if I try running make hello3, we'll see that, actually let me do a make clean first so we get all of the output, and then I'll do a make hello3. Now you can see that it actually did the same commands as we saw for hello2, right? Where we're compiling main.c into main.o, greeter.c into greeter.o, and then we're linking all three together to form, in this case, hello3. So now we should see, if we go out here in our directory, that we've got a hello3, and it's dependent on those two greeter and main.o's that were all constructed since we last modified the makefile. So this is decidedly arcane and hard to understand and hard to remember syntax, but it turns out to be handy in some cases, especially as the number of object files that you're linking together grows, and to avoid the kinds of errors that I mentioned before. I use these kinds of things in my own makefiles. I would not encourage you to start doing that right off the bat. I would stick more to just explicitly listing everything out as you get started using make. And once you feel like you have a pretty good facility with what's really going on here, then yes, for sure start coming and looking at some of these more arcane ways of specifying files. Thought about some other things I wanted to let you know about here. First of all, I'm going to get rid of this shortcut version of the build step for hello3, just because I don't want you to have to worry about those confusing meta variables. One other phony variable that's oftentimes helpful to have is something that lets you do some smoke testing. So you might create a test dependency, and if you want to test, for example, the hello2 file, you could make test dependent on hello2, And then the recipe would actually be, well, let's run hello2 and send it in foo bar baz. So now if I say make test, it runs that program and I can verify its output. Furthermore, because I made that test dependent on hello2, if I make a let me just remove main.o, or equivalently we could update main.c to be newer than main.o. But now I'm removing this dependency that needs to be present there. Because I told test that it was dependent on hello2, hello2 is going to be rebuilt in this case because I've removed one of the object files that's used to create it. So if I say make test again, you can see first of all that we recompile main, which also would have been the case if I had updated main, and then we relink hello2 before we run the test command itself. So that can be really helpful and handy. Another thing to keep in mind is that in order for make to know about dependencies, you've got to tell make about them. Let me just ensure that everything is current as of right now. I'll do a make all. Okay, that's cool. Now, if you recall back to when we wrote the source files for our hello2, we have our main.c, and it's depending on greeter.h, right? Greeter.h, you'll recall, was the header file that basically declared that greet function. And we want to use that in main.c because we're going to call the greet function, and we want to make sure the compiler can ensure that we're calling it in the right way. And we also used it in our greeter.c file because we want to make sure that the declaration from the header file matches the actual implementation in greeter.c. Now you might think that because the C compiler is including greeter.h in both of those source files, that if we changed greeter.h, make would cause things to rebuild. So let's go into greeter.h, and we'll just make a modification here by we'll just add a comment, forward declarations, something like that. So now we've changed greeter.h. If we go back down here and do our ls-lt, we can see that greeter.h is the newest file in the system. Now, just a second ago, I did a make all to ensure that everything was built, and I'm going to do a make all again. Nothing to be done for all, okay? Now, this is kind of an Achilles heel of make. All make knows how to do is look at files, figure out which are newer than the others, and then run some commands in response to the situation where the target is out of date with respect to the dependencies. It has no idea of C or inclusion or any of that kind of stuff. If we want to make sure that make knows about those dependencies, we have to tell it. So let's go back to our make file. And we're going to add some dependencies here that tell make about the relationship between the targets and the header files that they depend on. So we can put this pretty much anywhere we want. Let's just say that main.o depends on greeter.h. And we can also say greeter.o depends on greeter.h. Now I've already updated, as we can see here from our directory listing, I've already updated the greeter to be newer than any of those object files. So now with this updated make file, if I say make all again, why not? You can see that it rebuilds those things. Do it again, everything's cool. If I go back up here and change my header file to have just some new stuff in it, that makes it newer as far as make is concerned, do make all, and it's going to make those two files again. Again, back to the make file, I'm saying that the main.o file depends on greeter.h. In other words, we should remake main.o if greeter.h changes, and the same thing for greeter.o. We should make it again if greeter.h changes. So we can see here that these first two rules, or these first two commands, are the result of make detecting that greeter.h is newer than main.o and greeter.o. And then of course, because we're doing make all, we're asking make to construct hello2 as well as hello, and hello wasn't changed at all, so that's not a big deal. But it's also going to rerun the command that links together the newly compiled main.o and greeter.o to form hello2. It's also possible to combine these to simplify the makefile a little bit. If I have multiple targets that depend on the same dependencies, I can just list them here separated by white space. So I can move greeter.o into that same rule. And now if I were to update my header file again, get rid of that white space I just added, and then do make all, we'll see that the same rebuilding steps take place. So that's equivalent to those two dependency lines. Another thing that's helpful here, I've been kind of going back and manually making changes to that greeter.h file to sort of see what the effect is and make sure that the makefiles are working properly. There's another standard command called touch. Let me start by doing an ls-lt. We can see right now hello2 and greeter.o and main.o are newer than greeter.h. But the touch command basically says go out and just touch that file and make its modification date be right now. But don't make any changes to its contents. So if I say touch of greeter.h, nothing happens. Greeter.h's contents is exactly the same as it was. But if I do my ls-lt again, we'll see now greeter.h is the newest file in the directory. So that's a really helpful way. If the file doesn't exist and you touch a file, it'll create an empty file with that name. Some people like to do that. I don't really see a compelling reason for it because you can do the same thing in your editor. But if you want to just tweak the modification date to be right now, that's a very helpful way to sort of force things to rebuild or to test that your build file is doing the right thing. So if I say make all again, or just, well, yeah. If I say that make all again, it's going to do that rebuild. If I do make and all is the default. So there's nothing to be done. Again, touch of any of those files. So I could, for example, say, let's imagine that I went in and made a change to main.c. So touch main.c is going to just update main.c to be current, or to have a current modification time. And then if I do a make again, it should rebuild main.c into main.o and then relink hello2 because it depends on main.o. And that's what we see. There's a ton more stuff that Make knows how to do, lots of different crazy capabilities that can improve your workflow and your build reliability and convenience. Definitely worth investing some time as a developer to learn how to use it effectively. Certainly at the level of what we've looked at in the example makefile today, but there's a lot more to it. You're welcome to take a look at the online documentation or look at the manual page or the info documents that come with it. Really good tool to have in your tool bag.